Welcome to the University of Connecticut. My name is Ed Wazer, and this is Connecticut's Center for Applied Separation Technologies.
Our lab got started working in a process called electrospinning back in 2008. In 2017, almost 10 years later, one of my graduate students, Maksud Chowdhury, who's now has his doctorate and is working at Intel, he found a way to adapt our electrospinning technique to create an electrospray technique. So if you think about how membranes are produced today, they're produced using technology that's about 40 years old. We have limited offerings of what you can buy. You go to the store, and if you want to buy a reverse osmosis system for your business or your home, you're given whatever membrane they give you. Why wouldn't you want to buy a filtration product or a filtration system that was specifically tailored for your needs?
So this is our electrospray system, which we use to print membranes on supports. So what we have is a syringe pump on which we load a syringe with the polymer that we want to make into a membrane that's in liquid form. And then we push the liquid through this tubing into a capillary needle. That's a power source that basically once turned on would apply voltage to that needle, and that gets transferred to the solution, and then the solution explodes into small droplets when it gets collected on this drum. And once they're printed, we cut them to sizes and then use them to test for either reverse osmosis, a water filtration application, or a gas separation application. So the beauty of this process versus what's being used commercially to make, let's say, a reverse osmosis membrane, is you can dial in the thickness of the membrane, which basically affects your flux through the membrane. So the thinner the membrane, the more water you're gonna get through the membrane.
After the membranes are created, that's where I usually come in. I design systems so that we can test under high pressure, under high temperatures, and under conditions with flammable liquids, flammable gases. We design the system to actually make the membrane, and then behind me is a system that we use to actually test the membrane.
So our goal here is to show that we can actually take this process and scale it up to a reasonable size. So at the end of our project, we'll be able to print a membrane that's approximately 40 inches long, 14 inches wide, and that will be rollable into a small prototype element that we can test and show that the process can make membranes at scale. And if we can better disseminate membrane technology to more people so that more people use it, it betters the lives of everyone.